This lecture is about quantifying the location of an object. But before trying to answer the question, where is the object? Let us make sure that we have defined what kind of object we are prepared to study. This object will not expand or deflate, which, in most cases, means that the object is solid and rigid. It will not explode, so it will stay as one object for the duration of the study. It will not spin, which leaves the study of rotational dynamics to a more advanced physics course. It will only occupy one point in space. Now, this condition is a bit harder to swallow. After all, it sort of implies that the object has no volume. But you can reconcile this result with reality by limiting your search for the location of the object to one point on the object. For example, the location of the center of a ball. Since a ball is not expanding, exploding, or spinning, then knowing where the center is located pretty much tells you where the rest of the ball is. You could also use an approximation. If the object is very small in comparison to the space it is in, you can picture it as just one point in space, like a fly in a concert hall or a car along a 5-kilometer road. Yet another way to reconcile the idea that we will not be interested in the shape of the object, it is to recall that we are working with best estimates of measurements, and the error on the location of the object can include the size of the object. The next step is to choose a single point in space that we will call the origin of the reference frame. A landmark or a physical feature is normally used to pinpoint it. Example of possible choices for the origin could be the intersection of two streets, the city hall of a town, or the starting point of a race. Notice that all these examples have something in common. Their locations are fixed in comparison to their immediate surroundings. However, this is not a requirement for an origin. You could have chosen that wherever you are is where the origin is. In other words, you are always at the origin. This is not the easiest origin to work with, but it is not forbidden. Far from it. However, in this course, we will restrict ourselves to origins that are fixed in comparison to their immediate surroundings, and leave the special challenge of the moving observer to a more advanced physics course. We finally have all the requirements to be able to define a quantity that will quantify where an object is located. We will use the letter O at the origin and the letter capital X at the location of an object. Let us pick 2 points on the page. One will be our chosen origin, the other one the location of object X. We can create a vector with its tail at the origin and its tip at the location of the object. The vector will be our way of describing the position of the object. We will reserve the use of the letter name D with an arrow for quantities that are representing positions of object. The magnitude of the vector D is the distance between the origin and the object. The typical measurement units for position vectors are millimeter, centimeters, meter, or kilometers. The easiest situation to study at first is a situation where the motion of the object is restricted to a line in space. However, it is only easier if you make the right choices for the origin and for one of the reference directions. That is, if you restrict the origin to be a point on the line, and that one of the reference direction is set to be parallel to the line. For example, the object could be located here, so that its position vector would look like this. Since both the origin and the object are on the line, the vector position that you have created between them will be parallel to the line. Something that would not have happened have you chosen the origin at a point off the line. Now, since the position vector is parallel to the line, It is also parallel to the reference direction. It is parallel to x hat. It means that the vector position has at most one non-zero component. This is a one-dimensional problem. The position vector can be written in this special case like this, and the magnitude of the position is equal to the absolute value of its only component. An example of linear motion could have been the one of a ball thrown vertically upward, but here I chose the example of a motion along a straight road between Toronto and Montreal, the 401. The location of Toronto could be marked by the intersection of the 401 and Yonge Street, and Montreal would be located 600 kilometers away from Toronto. I will also indicate the location of Kingston, which is halfway between Toronto and Montreal. The chosen reference direction is pointing from Toronto towards Montreal. The position of Montreal, if Toronto is at the origin, is represented by this red arrow, and it would be equal to 600 kilometers x hat in component form. But if we switch the role of Toronto and Montreal, then we get the blue arrow, and it is equal to minus 600 kilometers x hat, because the vector is now pointing in the opposite direction to the reference direction. The position of Kingston, if the origin is at Montreal, looks like the green arrow. And since Kingston is midway, the position is equal to minus 300 kilometers x hat. Now, if we require the x component of the position of Kingston when the origin is at Toronto, then the answer is 300 kilometers. The vector position would look like this yellow arrow. But here, only the x component is required, which is a scalar. The next physical phenomenon to be defined is time. Its relationship with position will be examined in the next installment.